Hello and welcome to my presentation on how to answer question 4. As seen stated, 255 grams of neon gas occupies 3 litres at 122 Kelvin. Using the ideal gas law, calculate the pressure of the neon gas. So R, or the constant in this case, will be using 0.0821, and as we should all know, the ideal gas law equation is PV equals nRT as seen currently. So we're going to write each part down on the side. I'm going to see what we have and what we don't have. So pressure, we don't know, we're being asked to calculate it. Volume is 3 litres. The number of moles, you can work this out. It should be 12.637 moles. Now the gas constant we've already discussed will be 0.0821 in this case, and the temperature is 122 Kelvin. Now, if we rearrange the equation, we should get P equals nRT all divided by V. Substitute everything in and you'll have P equals 12.637 times the constant times the temperature, all divided by the volume. And the pressure should, now you can check by putting this into a calculator, should equal 42.19 atmospheres. Now for the second part of this question, we will be treating the gas as a Van der Waals gas, and this will require a different formula. So the second part of this question is treating the neon as a Van der Waals gas. So first of all we need to write down the Van der Waals equation, which is P equals nRT all divided by V minus NB and minus A times N divided by V all squared. Now again, if we write everything down on the side, we can see what we have and what we don't have. So again, we need to calculate the pressure, so we don't know that. The volume we do know, that's 3 litres. The number of moles, again, is 12.637 because nothing's changed, nothing's been added. The constant, again, we use the same one as last time, is 0.0821. The temperature, again, hasn't changed, so we're using 122 Kelvin. A is going to be 0.205 and B is going to be 1.67 times 10 to the minus 2. Now, if we substitute this in, which I will very quickly, or try to very quickly, you should have something that starts to look a bit like this. And then if we add the last bit on, which is all the way over here, all squared, your pressure should, if you put that into a calculator, and you can check, should equal 41.75 atmospheres. Now, the pressure, when you treated it as an ideal gas, was 42.19. Now, because there's not much difference between the two, you're perfectly okay to treat them. The third part of question 4 is 40 grams of helium is added to the previous container that contained the neon gas. The pressure and the temperature remain the same. And the question is, what is the partial pressure of the helium in the container? So the first thing we need to do is obviously work out the moles of helium. Now if you work this out, it should equal 9.9925, or if you want to round it, 10. Now we already know the moles as the neon in the container, and that is 12.637. If we add the two together, this should equal 22.6295 moles. The next step is to calculate the mole fraction of helium, and that will be 9.925 divided by 22.6295, which should, if you put that into a calculator, equal 0.442. The last step is to times this by the pressure. Now we already know the pressure from the previous question because we worked it out, and that is 42.19 atmospheres, meaning the partial pressure of helium in the container should be 18.65 atmospheres. Alright, so the next step is to calculate the root mean speed for the helium and neon and sketch the Maxwell-Boltzmann distribution for both. So we're going to start with the root mean square of neon. And the formula for this is as follows. Now, the gas constant we're going to use for this is going to be 8.31, and molar mass needs to be in kilograms, and this is all to do with joules and energy. So if we work this out for neon and we substitute everything in, we should get the square root of 3 times 8.31 times 122, which is the temperature of the system previously mentioned. Now the molar mass is going to be 20.179, that's really badly drawn, divided by 1,000 to make it kilos, and this should be 0.020179. Put that into your formula and it should look like this. Put it into a calculator and the value you should get out the other end should be 388 meters per second. That is the root mean squared value speed for neon. So we've calculated the root mean square for neon. That equals 388 meters per second. Now we're going to do the same thing for helium. So using the same formula, we're going to work out helium's molar mass, which is 4.003 divided by 1,000, which equals 4.003 times 10 to the minus 3. Now, you can just use the value of 4 because that 3 is very, very, very small. Substitute all the values in, you get 3 times 8.31 times again the temperature of the system, which is the same as at the start, all divided by the molar mass, and then you square root the whole thing. Put that into a calculator and the value you should get out at the other end is 872 meters per second. So for this system we have worked out the root mean square speed for both. So we know that neon is 388 meters per second and helium was 872 meters per second. So if we draw the Boltzmann distribution, So the graph should be the speed on the bottom in meters per second, and then on this axis is the probability of them being at that speed. So for Neon, it should look something like this, coming up, almost like a spike, with the root mean square speed being about that point. And then for Helium, it should be more of a bump on the graph, but it's shifted over, and the root mean square speed is about here.